For our project, we'll be testing the viscosity in different liquid substances as they slide down the board to see which one has a lower or higher viscosity than the other. First of all, viscosity is a property that is needed to describe the fluidity of the fluid. It's the state of being thick, sticky, and semi-fluid in consistency due to internal friction. The materials that we use for our project are poster boards and multiple liquids that consist of soap, mustard, ketchup, syrup, jam, vegetable oil, water, engine oils, which are synthetic and diesel engine oil, and vinegar. We use all of the liquid materials above for the first test at room temperature.
All fluids have different viscosities, and we will be testing those viscosities with fluids that we see in our everyday lives. Not only will we be testing their viscosities, but we will also be testing them at a room temperature, some in cold temperatures, and the others will be warmed up in a stove. We will be measuring different fluids, such as oils and household items like syrup, ketchup, and vinegar. We will also be testing engine oils. The engine oils we have chosen will be stored in the freezer, and then we will test them. Then test them at a room temperature, and for the household items, we will heat them up in a stove due to the fact that our microwave was not working. We will heat them to a certain amount of minutes and then test them. Then we will test them at a room temperature. We will use a cardboard as the plane to test them out on, and we will line up the liquids to see how long each item will take. The distance we have originally chosen is the 2-foot line. Then we will measure them at a 1-foot line if it cannot reach the 2-foot line. We will stop the clock for each liquid when it has passed the finish line.
For the second test, we use all of the liquid materials at 215 degrees Fahrenheit, except for the 2 engine oils due to safety reasons.
As the temperature rises, fluids will tend to lose their viscosity, just like when honey or syrup is heated up. It will slide down just like water at room temperature. That is because of their viscosity change. But what really is viscosity, you may ask? Well, it is the thickness or resistance of how long it will take a liquid to flow through an instrument called a viscometer. Mainly when liquids get heated up, they tend to move around very easily because of its molecules becoming very excited. It will basically unbind the molecules from each other, making them much easier to flow through themselves. Although the opposite will happen when it is cooled in a freezer. They will gain viscosity and become much harder to move around. That is because the molecules are no longer excited and basically have fallen asleep.
We first tested 9 different liquids in room temperature, and these are our results. Ketchup and mustard had the highest viscosity of all the liquids, which means their velocity will be the slowest. The higher the velocity, the slower the viscosity. As you can see from our results, ketchup and mustard didn't even pass the 1-foot mark. We then tested 8 different fluids that got heated up. These fluids can be classified as Newtonian fluids, since their viscosity is dependent on the temperature of the fluid. For our last viscosity test, we decided to freeze synthetic oil and diesel oil. As you can see from our results, the synthetic oil had very high velocity compared to the diesel oil, which means the viscosity was lower on the synthetic oil than the diesel oil.
If you have ever changed your own engine oil or watched the process, then you might have noticed the specific sequence of letters and numbers on the front of your oil container. The acronym SAE at the beginning of the sequence just stands for Society of Automotive Engineers. The following sequence after SAE, for example 10W30, contains two distinct characteristics about the viscosity of that oil. W in 10W stands for winter and not weight. The 10 corresponds to the oil's ability to resist thickening at 0 degrees Fahrenheit. Ideally, vehicles in cold climates in the north would require a 5W to 0W engine oil to guarantee engine performance during the winter. The number after the 10W indicates the oil's viscosity at 212 degrees Fahrenheit. The higher the number, the less the oil will thin at high engine temperatures. The 10W-30 oil would be ideal for a relatively hot summer and not so cold winter, much like the climate in the southern states. Oil thickening is sometimes bad for certain vehicle engines that have smaller spaces between the mechanical parts for the engine oil to move through. It can also put a strain on the oil pump. If the oil is too thin, it does not provide the required oil film thickness to separate metal surfaces, especially in the valve train. And when this happens, metal surfaces will eventually wear out and eventually destroy the engine. For our project, we are comparing the viscosities at room temperature and near 0 degrees Fahrenheit of two specific engine oils: synthetic oil and diesel engine oil. Our oil may not actually be at 0 degrees Fahrenheit because we lack the resources to match the conditions. The purpose of the video is to provide an idea on what the oil does at temperatures pretty close to 0 degrees Fahrenheit. We would also have liked to have done oil at 212 degrees Fahrenheit, but our group was not comfortable with trying to heat oil to that high of a temperature. Oil, synthetic oil, 5W20, used in mid to high performance car engines, and Valvoline diesel engine oil, 15W40, used in diesel engines. So synthetic oil is partially man-made and is engineered to reduce friction of the oil on the camshafts. It also does not have to be changed as frequently. Diesel engine oil is around the same price as synthetic oil and does not have the added benefits other than being a little thicker because of larger gaps in between mechanical parts. Diesel engines are a little bigger in size than the engines that synthetic oil is usually used for. Our initial room temperature run had synthetic oil flowing across the board easier than a diesel engine oil, leading us to conclude that synthetic oil is less viscous than the diesel engine oil, probably because it is a little thinner than diesel engine oil to account for smaller clearances in the smaller engine sizes. For our second run, we took the same amount of synthetic and diesel engine oil and stored it in a deep freeze that was set at around 0 degrees Fahrenheit. So the synthetic oil again ran smoothly across the bore, while the diesel engine oil seemed to have thickened up, and this flowed a lot slower than the room temperature run. This experiment concluded a couple things about the oils used. The synthetic oil 5W-20 performed better in cold conditions because of the 5W standards it was rated for. Although the 15W foil did not perform well in the cold, we can conclude that in warmer conditions the diesel engine oil would perform better and not thin out as quickly as possibly the 5W-20 oil because of its high temperature rating of 40. This concludes our project. I hope this video has enabled a better understanding of viscosity through household fluids and provided an understanding of engine oil viscosity. Special thanks to Lamar University and the Department of Mechanical Engineering and Professor Ajit Patki.